Hello, greetings. Let's take a look at problem 2, which is our second problem involving unit conversions. So the equation below gives the boiling temperature of isopropanol as a function of pressure, where T is in Kelvin, P is in bars, and the parameters A, B, and C are as follows. Obtain an equation that gives the boiling temperature in degrees Fahrenheit as a function of log P, natural log of P, with P and PSI. Hint, the equation is of the form of that. But the constants A prime, B prime, and C prime have different values from those given above. Okay, so essentially what we're given here is Antoine equation, right? And so probably you've seen Antoine equation before, an equation in which you have an input of temperature and it outputs the corresponding saturation pressure for pure component fluid. Here though it's solved for T. And so how I'm going to look at this is essentially I have a function that takes an input of P, here pressure in bar, and it returns a temperature in Kelvin. Okay, and so the constants A, B, and C, so they're constants. They don't really have units, right? But the units are the values are dependent on the units of T and P. All right, so when you look up constants in a table so if you have a table of Antoine constants, right, there's not really units for the Antoine constants. The units provided are for T and P along with the functional form used for your Antoine equation. So here we're given constants A, B, and C for the case of temperature in Kelvin and pressure in bar, and we're asked to map it so that rather than taking an input of pressure in bars, we take an input of a pressure in PSI, and we return, rather than a temperature in Kelvin, a temperature in degrees Fahrenheit. Okay, so we're going to have to convert from our pressure, rather than take an input in bars, we want an input in PSI, and being returned, rather than a temperature in Kelvin, we want temperature in degrees Fahrenheit. Okay, so we're going to have to take it, we're going to have to do conversions for our pressure and temperature, and then also we're asked to convert our log of base 10 to natural log. Okay, and so as a note, this is my second attempt. So I posted a screencast earlier, but there's a apparent issue with my solution. I believe it's with my unit conversion for pressure, and so here I'm going to try and do it again. And I also have MATLAB open on the screen below that we can use to test my solution each step along the way. Okay, so let's do it. Okay, so I'm going to take a note of what we have. Okay, so we're starting with our expression where temperature is in Kelvin. So I'm going to write a subnote of Kelvin. Then I have B over A minus log base 10. Log base 10 of P, where P is in bars, minus C. All right, so we need to do three conversions. Pressure from bars to PSI, temperature from Kelvin to degrees Fahrenheit, and then also log base 10 to natural log. Okay, so let's do it. So since I think it's the pressure conversion I got wrong last time, I'm going to start there. All right, and I want to convert my pressure from bars to PSI. Okay, and so what I mean again here is rather than taking an input of pressure in bars, I want an input of pressure in PSI. Okay, so imagine now I have an input of pressure in PSI. To get it to work with this expression, I'm going to need to convert from PSI to bars. Okay, so I'm going to go over to a web browser and I'm going to look up convert bar, okay, bar to PSI. Okay, so 1 bar is 14.504 PSI. Okay, so I have the conversion factor 1 bar is equal to, is it 14.504? We'll just do 14.504. Okay, so 1 bar is equal to 14.504 PSI. So that's supposed to be erased. All right, so if I want to give an input of pressure in PSI and then convert that to bar to use with this expression, okay, so what that would be then is, let's see, so 1 bar is 14.504 PSI. So my pressure in bars, okay, would be equal to 1 over 14.504 times my pressure in PSI. All right, so if I input my pressure in PSI and I divide by 14.504, I obtain the corresponding pressure in bars. Right? So, the significance of this is, 1 bar is 14.504 psi, right? So this is, bars per psi, right? So if I input a pressure in psi and I multiply it by my conversion factor for psi to bar, I get a pressure in bar. Okay. Cool. So in doing so then, if I plug in this expression for p bar up here, okay, I now have that T Kelvin is equal to B over A minus log base 10 of, okay, so now for P bar, I'm going to plug in 1 over 14.504 times my pressure in PSI, bam, minus C. Okay, so now to look at this term in the denominator a little bit more. Okay, first I'll do, log trick 1, where remember the log of a product of two numbers is just equal to the log sum of those two numbers. Okay, so my temperature in Kelvin then is B over A minus log base 10 of 1 over 14.504. Okay, and so remember this is minus. Okay, so plus log base 10 of my pressure in PSI minus C. Okay, so distribute. Just make sure I have it right. Yep. Okay, so this would be minus log base 10, 1 over 14.504 minus log 10, my pressure in PSI, minus C. Okay, and then the last thing I'm going to do is this is 1 over 14.504. So if I take the inverse, right, bring up a negative 1 here, bring it down, so playing again with log rules, that'd give me B over A plus log base 10 of 14.504 minus log base 10, my pressure in PSI, minus C. Okay, and so I'm going to do in step 1 then is I'm going to define, we'll call it A2. Okay, log base 10 of 14.504 is just a constant. So I'm going to let A2 equal log base, A plus log base 10 of 14.504. Okay, so now I have an Antoine equation that still gives me temperatures output in Kelvin, temperature output in Kelvin, but now I have, using this new constant A2, I can give in input pressure, I can use as the units of my input pressure, PSI minus C, okay, where the values of B and C are unchanged. All right, so now to check this, I have MATLAB open. Okay, so what I've done here is here's my original constants. And so as a reference, if I have a pressure of 1 bar and I plug it into my original Antoine equation, I get a temperature of 354.2797. Okay, so what I'm going to do here, okay, is we have now defined this A2. Okay, A2 is going to be equal to A plus log 10 14.504. Okay, 14.504. All right, and so a trivial example, but again, we had said that 1 bar was equal to 14.504. Okay, so what I want to see then, okay, so this is for, okay, so now what should happen is if I were to retake this expression, well, let me define a pressure in PSI. Okay, so 1 bar, a pressure of 1 bar is 14.504 PSI. Okay, so what should happen is if I take our original equation, okay, and I update my constant A to now be this A2, I can now give my input pressure in units of PSI. Okay. And so if I do that, okay, I get the same temperature, 354.2797. Okay, so this constant A2 is correct, right? So again, all I've done is I define this new constant A2, which gives me a new updated Antoine equation that uses this constant A2 instead of A, and an input pressure in PSI rather than pressure in bars. And so rather than giving an input of 1 bar, I give an input of 14.504, which is the equivalent of 1 bar, just to confirm that I'm still getting the same temperature. Okay, so first part, things are working right. Okay, good. So let's move on. And I'm not sure I'm getting a Dropbox notification on there, but let's stick with pressure. Okay, so that was the first part. Okay, so now step 2, let's continue with the pressure term. Let's convert log 10 to natural log. Okay, and natural log is nothing more than log base E. Okay, so for this one, we've got to dig deep. We have to remember our change of base rules. Okay, and please note, I forget this all the time and always have to look it up. But if you look it up, what you should find is that log base B of A is equal to log base X of A divided by log base X of B. Okay, and so how we'll use that here, okay, is since we're interested in log base E, or natural log of P, okay, I'm going to write log base E of P in PSI, okay, is equal to, okay, so B is E, A is PSI, okay, so now for my base X, I'm going to use log base 10, okay, which is what we're starting with. So log base 10 of A is PSI, pressure in PSI, divided by log base 10 of B is E, where log base 10 of E is just a constant, okay, and log base E is just natural log, so I'm going to say that's equal to natural log of P in PSI. Okay, so solving for log base 10 of PSI, which is what I'm starting with, okay, log base 10 of my pressure in PSI is equal to log base 10 of E times natural log of my pressure in PSI. Okay, so now I'm going to plug into my original expression log base 10 of PSI with this, right? And what this should be is, a value of log base 10 of P is equivalent to log base 10 of E times natural log of pressure in PSI. So plugging that in, okay, now I have TK is equal to B over A2, okay, minus, now I'm going to write in log base 10 of E times natural log of P in PSI, and that's minus C. Okay, cool. All right, and so now what we're going to do next is we want an expression that takes the form of an Antoine equation where it's b over a minus log p minus c. Okay, so I don't want a constant times my log p term. So how I'm going to get rid of this constant is that I'm going to do our favorite trick of multiplying by 1. Okay, so let me just move the minus c off. Okay, so I'm going to multiply by 1, or in this case, rather than 1, I'm going to write log base 10 of e over log base 10 of e. Okay, where log base 10 of e is just a constant. Okay, and to further clarify, I'm going to write it as 1 over log base 10 of e divided by 1 over log base 10 of e. Okay, so if I do that, okay, and distribute, okay, my numerator, I'm going to have b over log base 10 of e divided by, so a2 divided by log base 10 of e. Okay, again, log base 10 of e is just a constant, minus, okay, log base 10 of e will kill the log base 10 of e term, and so I'm just left with log of psi as I desire. Okay, and that's minus c. Okay. So next, I'm going to define, so I'd call that a2 for some reason. Let's introduce now constant b3, our third step, our first step is what we started with. Let's define b3 is equal to b divided by log base 10 of e. Let's let a3 is going to be equal to a2 divided by log base 10 of e. And in doing so now, my expression is tk is equal to b divided by, b3 divided by a3 minus natural log of p and psi minus c. Okay, so now let's do another check to make sure that we have got this right. Okay, so I'm going to go down here, and so my MATLAB code, this is all good. So here's my expression using psi. Okay, but what I'm going to do next is I'm going to define some new constants. We're going to say b3 is equal to b divided by log base 10, and e I raise exponential of 1. Right, so if I come down here, right, exp is MATLAB's e, right, e raised to power, so I'm going to do e raised to power 1. So I have b divided by log base 10 of e. Okay, a3, a3 is equal to a2 divided by log base 10 of e. Okay, so now my check is, I'm going to copy this equation. Okay, so basically I want to keep my input in psi, this 14.504. Then I'm going to date this to b3, a3, and instead of using log base 10, natural log. Okay, so I want to confirm that when I have now here natural log of p and psi, along with these new constants b3 and a3, I'm still getting the same temperature when my input's this 14.504 psi or 1 bar. Okay, so running, good. I'm still checking out. I'm still getting the same value. Okay, so good. I'm still good. I'm good. All right, so that's the first part. Okay, so now step 3. Okay, we just need to make it so that we take our output, which is in Kelvin, and rather than using Kelvin, we want to convert to degrees Fahrenheit. Okay, so what I'm going to do is I'm going to take this in 2 steps. Okay, and you could do either way. First, I would either take this as converting from Kelvin to Rankine, or Kelvin to degrees C, and then say you have degrees C, you can convert to Fahrenheit, or Rankine, you can convert to Fahrenheit as well. Okay, either or. Okay, so let me first do, let's say Kelvin to Rankine. Okay, so this one I'm going to have to look up again. So let's do Kelvin to Rankine. Let's see if I can get it. Metric conversions. do give it to you. So Kelvin to Rankine, so the temperature in Kelvin, or Rankine looks like it's the temperature in Kelvin minus 273.15 times 180. Oh boy, at that point I might as well just do Kelvin to Fahrenheit. Let's see what they have. Here we go. We'll just go for we'll just do it all then. Okay. So let's just do temperature. Oh. Okay. So if I go from Kelvin to Fahrenheit, okay, the formula that we're given is temperature in Fahrenheit is equal to the temperature in Kelvin times 9/5 minus 459.67. Okay, so I mean we could tackle this a number of ways. One is, well, here TK is equal to this, all right? So I could substitute in for TK this, and then distribute. That's probably the easiest. Or I would solve for TK and then plug that left hand side in up here and then resolve for TF. So I think the easiest thing is going to be TK is equal to this. So plug this in here for TK and then simplify. Okay, so let's do that. So TF then is going to be equal to, I'm going to write this as 9/5 times, okay, and I plug in everything I have for TK. So TK is B3 over A3 minus natural log of pressure and PSI minus C, okay, and then plus or minus 459.67. Okay, now we just have to simplify. So TF is equal to, let's distribute the 9/5. So this would be, I could write this as 9/5 times B3 divided by A3 minus log PSI minus 9/5 times C minus 459.67. Okay. Cool. So let's define some new constants then, essentially. So this is our last step. So I'm going to define B prime. B prime is going to be equal to 9/5 times B3. A prime is just equal to A3. I don't have to do anything there. Now C, okay, C prime, okay, what's C prime going to be equal to? So what we need to remember is in the equation that we're told for, right? Remember this term is minus C, right? It's all the way back up here, right? Minus C prime. Okay, so remember that it's minus C prime. Okay, I'm going to define C prime is equal to, okay, the sign's going to be opposite then since it's negative, or minus, 9/5 C plus 459.67. Okay, and in doing so, that gives me an expression where the output temperatures could be in degrees Fahrenheit. B prime over A prime minus natural log of pressure in PSI minus C. Whew, that's a lot. All right, now to test it out. Okay, so first things first is so far we have this code working where we get temperature, or we have an input of a pressure in PSI and we get a temperature out in Kelvin. We've been getting this 354.2797. So the first question is, let's convert that temperature from Kelvin to degrees Fahrenheit. So then we have a reference temperature in Fahrenheit, and then we'll try this expression with our new constants A prime, B prime, and C prime, and see if we get it to work. Okay, and hopefully it does. Oh, I'm confident it will. Okay, all right. So our temperature conversion. So let's do it in the command window. So if I wanted a temperature in degrees Fahrenheit, my reference is going to be my temperature in Kelvin times 9/5 minus 459.67. Okay, 178.0334. All right, so now what we're going to do up here, okay, I'll do A prime is AP. A prime is nothing more than A3. B prime is 9/5 times B3. And C prime is equal to 9/5 times C plus 459.67. Alright, so now what should happen, okay, is our new equation gives an output of temperature in degrees Fahrenheit with constants B prime, A prime. We want natural log of pressure in PSI, and this would be minus C prime. All right, so now we have natural log of our input pressure in PSI, new constants B prime, A prime, and C prime, and that should yield temperature in degrees Fahrenheit. So if we keep working with this input pressure in 14.504, if I've done everything correctly, I should get a temperature of 178.0334. Okay, so let's see. So if we run it, I get the same 178.0334. Got it. Okay, so it checks out. Got it correct. Phew. All right, so hopefully now you can use that to get problem 2 working correctly.